Hello, this little video is on equivalence relations. It's a very useful gadget in mathematics, opening quite a few cans. So let's start with what a relation is. A relation on a set X is, well, formally is just a subset, call it R, of the Cartesian product of X with itself. So this is just a collection of pairs of elements from the set X. So let's write that little x is equivalent to little y for elements x and y from X. If and only if the pair xy is in this relation. With this notation it's easier to phrase what is an equivalence relation. A relation R is an equivalence relation if three properties are satisfied. So if the first one is that the pair XX is inside the relation. So this is a relation on X, capital X, for any little element X. Well, in terms of this twiddle notation, it's just saying that any X is equivalent to itself. Second property is that if the pair XY is in R, then the reflected pair YX is in R. In terms of this equivalence notation, this is the statement. So if X is equivalent to Y, then Y is also equivalent to X. And the last is assuming that we have two pairs with one thing in common. The last component of the first pair is the same as the first component of the second. Then we have a conclusion that X and Z, so the first component and the last component from the pairs put together, is in the relation. In terms of this relation sign, X and Y are equivalent and Y is equivalent to Z, then it's called transitivity, X is equivalent to Z. So these are really equivalent statements, but yeah, we can write it as one direction implication, but it can be flipped over to the other direction. So these three properties make a relation an equivalence relation. What is so nice about them is here we can form what are called equivalence classes. Of any element, and just it is what it is, saying we look at all elements which are equivalent to little x, and that is a subset of X, of course, and it is important part that is a non-empty subset because X itself belongs to it by the first property. And so any element of our set is in one of the equivalence classes, namely in the equivalence class of itself. But what is more is that equivalence classes are either coincide or do not intersect. So the whole set is just joined. This is to stress that equivalence classes do not intersect. It's joint union of equivalence classes for a fixed equivalence relation. So that is going to be a very useful property in many situations. I'm not going to go into examples of concrete equivalence relations. Rather, I will do an example illustrating how restrictive these three properties are for a relation. So that will be an example of counting the number of equivalence relations compared to the number of all relations. So let's look at not one element, that would be too trivial, but a two element set. Let's think of elements as say numbers 0 and 1. So relations on the set X we count first, and they're just subsets of the Cartesian product. So we are looking at the power set, the set of all subsets of X Cartesian product with itself. And to count them we have all the tools available now, so that is counting the number of elements in the power set is as good as raising 2 to the power of the cardinality of this Cartesian product, and that is nothing but the square of the size of X. And in our case the size of X is 2, the cardinality is 2, so we're raising it 2 to the power 4, which gives us 16 relations in total. So it's a bit too much to list them all on this leftover of the paper, but it's easier to list equivalence relations on X, just according to this general principle that X broken to disjoint union of equivalence classes is as good as equivalence relation on it. We can look at how many ways can we break X into a disjoint union of things, of classes which are themselves non-empty. So we're looking at decompositions of X, set theoretic partitions into parts non-empty. And the first such is, well, we only have 2 elements to distribute between the classes, so we can keep them in their classes, separate classes, and that is always possible for any X. So any element is just its own equivalence class. That is sort of a trivial equivalence relation where nothing is equivalent unless it is equal. And another possibility is to keep everything in one class, so everything is equivalent to itself. Again, for any size set it is possible to define, and that's another trivial extreme where everything is equivalent to anything else. But for a 2-element set, these are the only 2 possibilities. So we only have 2 equivalence relations comparing to the total 16 possible relations on our 2-element set. So equivalence relations are really rare, and really rare but very helpful in many situations. So that is it. See you later.